Bueno, como sabéis, estamos aquí porque tenemos hoy la oportunidad de celebrar un seminario más con la frecuencia habitual, ¿no?, que seguimos en el programa de doctorado de Ingeniería de los Recursos Naturales. En este caso es una actividad que hemos organizado en colaboración con la Cátedra de Cambio Climático y, por supuesto, con la colaboración de Mario, que está aquí a mi lado como profesor investigador del campus, experto en estos temas de energía marina y demás que vamos a tratar de hoy. Y por si fuera poco, tenemos el placer y el privilegio de tener a la profesora Imen Turki, de Miniuco. Bienvenida por estar aquí de la Universidad de Rouen, Normandía, en Francia, y es experta, como vamos a ver en unos minutos, en riesgos ambientales ligados a riesgos costeros, ¿no?, ligados al cambio climático y a todos los temas que transversalmente no corresponden a gran parte de las tesis doctorales de las que hacéis muchos de los que estáis conectados. El seminario, como siempre, está abierto a gente que no formáis parte del programa de doctorado, ¿no?, que hay unos cuantos inscritos. Aquí en persona estamos, bueno, 10 personas, pero online estáis pues al menos otras 2 docenas más, si no recuerdo mal. 23 ahora mismo estáis conectados. Con lo cual, bueno, desde el punto de vista del número de asistentes, pues el seminario ya es un éxito y seguro que lo va a ser también desde el punto de vista del contenido. Bueno, Mario especialmente, con mucho cariño y aprovechando la oportunidad de que el programa Ingenim, ¿no?, dio la opción a Imen de estar aquí estos días, pues lo han preparado con esa idea, ¿no?, que resulte, por un lado, estimulante a nivel científico para los que trabajáis en temas parecidos y, al mismo tiempo, estimulante a los que, para a nivel más divulgativo, os pueda interesar lo que ellos vayan a contar, aunque vuestras tesis no sean exactamente de estos temas. Así que nada, me acompaña Candela, que es directora de la Escuela de Ingeniería, que siempre nos apoya un montón en todos estos temas. Así que le cedo ya la palabra y en breve os dejamos con la protagonista, que no en absoluto somos nosotros. Primero es Imen y luego Mario, que también me interrumpe.
Eso es, nada. Muchas gracias, lo primero de todo, por la oportunidad de estar aquí acompañando en representación de la escuela. Bueno, pues vemos en calidad de directora de la Escuela Politécnica de Mieres, porque al final, bueno, pues tenemos una conexión directa con un instituto como es el INDUROT, una conexión directa con un programa de doctorado como es el DIRENA, que está gestionado desde este instituto, porque al final muchos de nuestros estudiantes, los egresados, también continúan su formación académica en él. Y luego, pues encima con la Cátedra de Cambio Climático, que también está aquí ubicada. Además, el tema de la movilidad, como ha mencionado José Luis, con la Alianza Ingenio, de la cual forma parte de la Universidad de Oviedo, en este caso, la Universidad de Rouen, y que ya tuvo la oportunidad, Mario, de acudir allí a visitar la universidad. Y bueno, pues es un placer poder tener a Imen Turki con nosotros, devolviendo un poco, ¿no?, esa visita dentro del programa. Nada más, tampoco quiero alargarlo más allá y estamos deseando escuchar.
Muchas gracias por la invitación. Muchas gracias por esta invitación. Estoy muy contenta de que estéis muchos online aquí en presencial. Lo siento, voy a hablar inglés porque es más fácil, creo, pero después las preguntas pueden estar en español, puedo responder en español. ¿Ok? Espero que está bien para todo el mundo. Ok. Entonces, me presento en breve. I am Imen Turki. I am associate professor in the Rouen Normandie University in the research units working on environmental issues from coast to riverine and watershed, basically the interface from the sea to the continent. And I am here now to present you some insights related to the local impacts of coastal hazards and their relation to climate oscillations. And then I will underline some state-of-the-art of that, the solutions and the adaptation strategies that could be taken to overcome such problems of hazards. So my first part of the presentation will focus basically on coastal hazards and resilience. So I will try to show some insights related to this. So coastal hazards, climate change, we know a lot about this in news, in many like in many documents, in our real life. So climate change is already pervading our daily lives and directly contributing to humanitarian emergencies, including floods. What is really the relation between this, the climate change, these coastal hazards, and then our actions and our roles as a human, okay, as a researcher to address this point and to discuss about it and to overcome this problem. So I will start this part basically, but by showing you what we can observe in our real life. What we can observe, it's not, sorry, just. Yeah, we can observe. So we can observe many risks of many hazards, and when that hazard is added to some climate, some environmental systems with many issues, we speak about the risks. So it is related to water overflow, okay, flooding, and marine submersions. Other risks related to extreme waves. We can see as well cliff slides and other torrential discharge, like we can see here. I have taken many some hazards from different parts in the world to show you what we observe in our life and how these events, many like with many impacts, very local in time and space, is related to many other complex phenomena. So, all such hazards are basically related to some, like several phenomena, mechanisms, and such mechanisms I can mention the increasing temperatures, and here I will stay here, maybe it's better. So what we can see here, it's if we take the evolution of the temperatures in the world, okay, so we see like we have like red patterns, and such red patterns are more pronounced in time, okay? So we have increasing temperatures. Sorry. And then if we take these temperatures and we look for the distribution in time, we have the green line, and then we can quantify these distributions and its evolution in time. So this green line will move to the purple line, or the purple Gaussian curve in time, to in the line and to highlight more warmer weathers and more high temperatures, as you can see here. We can see as well, like the rising sea levels in years, as we can see here, and these phenomena or these mechanisms is continuously increasing in time, as we can see here, and the prediction of the GIEC of the IPCC group like highlights the importance of this increasing using the pessimistic scenario and the optimistic scenario. As we can see here, the optimistic scenario, the blue lines, and the pessimistic scenarios, the red lines. And we have a very a significant increasing of sea levels until 2100. So how can we assess coastal impacts? And to do this, we have to focus on many aspects, of course, but basically the severity of hazards, of risk, and then the characteristics and the issues of coastal systems. So you have both sides. The hazards, the hazards induced by the drivers, and then the system which will receive these hazards. So how can we really define cost on the coastal systems? The coastal systems could be defined by very complex systems between two compartments, continents and sea and oceans, and this part, this interface is exposed to several mechanisms, complex mechanisms. But at the same time, this part has basically many functionalities. So what are the main functionalities of the coastal systems? We can summarize all the functionalities of the system, of this coast, by three. The first one, fortunately, we have a coast, because the coast is very important for the dissipation of energy, and the energy is dissipated over a decreasing slope, okay, here, and all the energy coming from the ocean is dissipated close to the coast to reduce the effects of this energy and all the hazard or the risks related to the urban zones and etc. And then the second functionalities are ecological, okay, like it's excellent environments promoting the development of many fauna and flora and other species. And the third functionality, which is very important as well, like it's an excellent environment promoting users, tourism spots. So protecting our systems or our coastal systems is preserving all the functionalities as a defense, ecological habitat, and users. How can we do this? And what are basically the main drivers responsible on the instability and the vulnerability of the different functionalities? So, to understand how can we protect our coast, just a reminder that we have different coasts. The coasts are very different. We have muddy, vegetated coasts, we have gravel coasts, cliffs, sandy beaches, of course, and we have islets. And for each systems, the intrinsic or the internal characteristics are very important and should be considered to understand the response of the coast to the different drivers. So, coast in the world, some statistics, as you can see in this map, we have in yellow color all sandy coasts, muddy coast in brown, cliffs, vegetated, and in red others. So we see here that most of coasts in the world are sandy beaches. And the problem here that other statistics, according to other statistics from previous work, that the coastal retreat or coastal instability is more observed in sandy beaches because it's so easy to erode sands than erode ground. So we see here, like in red points, retreating features in many coasts in the world. So why coasts are retreating? Why? So basically, what we have to look on different, as I told in the beginning, in two parts. The physical drivers contributing to the hazard, the instability of the coast, and then the coast in itself and the characteristics. So the physical drivers contributing or to this risk, are very complex. And the problem here that we have a nonlinear interaction between all processes from very processes at short scales like storm surge, wave setup, swash, and others, and other processes with long-term trends as mean sea level or sea level rise. So we have interactions between different mechanisms, and all mechanisms are operating at different time scales. So it's very complicated. And understanding the final response to the coast like means or needs to requires like an understanding or a significant understanding of all the drivers. So we can see here some examples. For example, if I take flooding as a coastal risk, so flooding here, it could be induced by some marine mechanisms like wave run-ups and others, but in other places where the connections between ocean drivers and fluvial activities, it's very important. For example, you can have some floods, fluvial floods and storms. And when we have cascading events or concomitant events between both of them, we speak about compound flooding. And we have a lot of such mechanisms everywhere, because we have, like, especially during winter seasons, where we have two extremes, and the concomitants between two extremes induce this type of compound hazard or compound risk. So, how the coast can respond to all physical drivers? So, in this response, or to quantify, assess this response, we have to look for the severity of these drivers and the vulnerability of the coast. To which extent we can consider that our coast is vulnerable, and why, and what are basically the main components contributing in this vulnerability. So I take the most famous examples: flooding, instability, disturbance of everything, the physical parts, but always the societal parts, the economical parts, everything. So it's really like a combination between many components in our life. So we speak about coastal resilience. What we mean coastal resilience, and how we can jump from coastal hazards to coastal resilience. So when we have such physical drivers and very severe physical drivers, the coast will respond to them. Okay, and in its response, it depends on its vulnerability. When the vulnerability is more important, the coast cannot resist to these such drivers, and speak about, like, the coast cannot be resilient and not really overcome such drivers or the instability induced by such drivers. So I will take some examples, very, very simple. We have done this manually, okay? If we will focus on the coast, okay, here we have the energy. We have this when the slopes is decreasing, have some vegetations, and here we have the urban components. Okay, so when this coast will be exposed to an energy, extreme waves, storms, what's happening? I put this in I put the state, or I describe it by this curve. I have the x-axis of the time, and the y-axis is the system, the state of the system. So here, the red arrows is the forcing, okay, and then the system will respond to this forcing, and we have three options, okay, to respond to such forcing. The first one, okay, like we have a perturbation, the red arrows, and then we have pre-perturbation, during the perturbation, and after perturbation. And the systems could respond to this perturbation through three options. The first one is this one. The system is resistant, and the changes are zero, no changes. The system is not vulnerable, is resistant, and is not we have any response to this perturbation. The second one, the system is so vulnerable and the forcing is so severe, so we have to collapse. Okay, simple. And the other options or the other possibilities, it's resistance, as we see in the blue part, and this it's resilience. And the system is resilient, like the system will take a time of adaptations to be resilient. Like the system will adjust itself to be resilient to the forcing. Okay, so we have three options. The system is unstable. It could be it's like can maintain its state, or it can change, adjust its states, function on its characteristics and the different physical drivers. So yeah, so we can ask, but which options and how the system will respond to the physical drivers. The options selected will depend on two parts, very crucial. The first part is the external conditions and the severity of all physical drivers. So when it's a balance between the severity and the system, and then the internal conditions. Okay, if the system presents, for example, many components increasing its vulnerability, so its response could not be a resistance or resilience to be set up. Okay, so we can define as a resilience like the ability of the coast to recover from disturbances and adapt to changes induced by climate drivers. Climate drivers, storms, sea level rise, high free activities, and others. But also anthropogenic activities. And when I say anthropogenic activities or actions, all actions related to our action to human, okay, like the constructions, nourishments, and others, okay. So why this, or how? What is the role of this resilience? Is basically to maintain the mitigations of coastal stress and ensure the effective functionalities over time. So here, when we speak about a resilient system, these systems can maintain all the functionalities, including defense, habitats, and tourism activities, and everything. So the system is maintained, is preserved. Okay. So I take an example here. If I will take an example of a resilient coast. How it's managed in the reality. So this coast, I will apply a perturbation. We see some retreats, but it's still resilient. What's happened in the reality that we see in the blue curve, it's the evolution of the systems, initial stage here, and then the shift, like the red part, shift, we have changes in the resilience. So the system cannot stay in its current stage. It is obligated to switch to another stage to maintain this resilience. It's another way to be maintained, So we have a shift, and then after the perturbation, and the final stage, as you can see here, it's another state of the systems. So when this occurred, it's occurred when the perturbation exceeds the when the perturbation exceeds the resistance of the system. Like the system is resistant, and when this system receives very severe perturbations, and its resistance is not able to receive this severity, you will switch to another part. You will switch to another type of resilience, another stage of resilience. So a resilient coast, like it's less vulnerable and it's a stable coast. And it's what we are doing. I will show in the next part of this seminar that with all the government, environmental organisms, with all with others, what we are trying to do, increasing the resilience of our coastal systems to face the effects of climate change. So, according to the national oceanic and atmospheric administrations, coastal resilience is the ability to adapt to changing conditions and withstand and rapidly recover from disruption due to emergency storms, basically in our case. So, in to face this, managers in coastal communities need to understand their existing vulnerability. So, to which extent the system is vulnerable, and how can I adapt to this vulnerability? So, to which extent the system is vulnerable, and how can I adapt to this vulnerability? So, to which extent the system is vulnerable, and how can I adapt to this vulnerability? So, to which extent the system is vulnerable, and how can I adapt to this vulnerability? So, to which extent the system is vulnerable, and how can I adapt to this vulnerability? So, to which extent the system is vulnerable, and how can I adapt to this vulnerability? So, to which extent the system is vulnerable, and how can I adapt to this vulnerability? So, to which extent the system is vulnerable, and how can I adapt to this vulnerability? So, to which extent the system is vulnerable, and how can I adapt to this vulnerability? So, to which extent the system is vulnerable, and how can I adapt to this vulnerability? So, to which extent the system is vulnerable, and how can I adapt to this vulnerability? So, to which extent the system is vulnerable, and how can I adapt to this vulnerability? So, to which extent the system is vulnerable, and how can I adapt to this vulnerability? So, to which extent the system is vulnerable, protect my systems and reduce this vulnerability to increase its resilience. And develop appropriate adaptations and mitigation plans for changing future conditions. That's our objective, like deploying and developing appropriate adaptation and mitigation, adaptation strategies. So this coast is resilient, but it should be sustainable. How is the coast is resilient and sustainable? Sustainable in time. So my coast is sustainable when I combine all the components: environmental, societal, and economical components. Like, to ensure this sustainability, I have to integrate everything. It's an integrative approach to understand, to maintain my systems, all my users in the beach, the economical activities and everything. It's like a package, okay? So that's why I need, and maybe you heard about it, sustainable development, sustainable management. How can I develop this sustainable management? It's basically, I have to combine the planifications, like the different steps required for the systems, and the adaptation. What are the adaptations that I can propose to adjust my systems to the different effects of climate change? So this needs a very significant coordinations and awareness. And then preservation of functionalities, as said before. So preserving the coast is preserving all the functionalities. We have to obtain everything that we are using to obtain, like defense, floor, and everything. And then we can speak here about la gestión integrada de zonas costeras. Okay, I think that you know this. Coastal management. So it's a management. Toda una gestión. It's a management. And for this, it's very crucial for the mitigation of climate change effects. So, okay, fine. So how can I know, or how can I assess this resilience? My coast here, is it resilient? I don't know. How can I do it? So it's maybe it's a philosophical word when I say about resilience, but to make it operational and actionable, I need to use some indicators. I say this, or I call this resilience, of indicators of resilience, or indicators of vulnerability. So when we have these big waves, okay, coming to my coast have some vulnerability to this energy and have as well some resilience, to which extent he can resist to this perturbation. So that's why we have many indicators. I will show you this after. So we have to implement them, to classify them, and to look for the prioritization of them. It's not the same when I am assessing the resilience of harbors, okay, or other natural systems, or other systems where the human activities are very important. I can take example Cadiz, Malaga, where we have a lot of maritime structures, and the vulnerability is not the same as other beaches, like in Santander or in Asturias or others. Okay, so we look for the impact of the indicator, the pertinence of the occurrence of the indicator, and the applicability. I will give you here some examples of indicators, basically geomorphological, ecological, anthropogenic, physical, economical, and social. So which indicator should I use? Very good questions. Basically, it depends on your objectives of the study, our focus of the study. But okay, more indicator, it's better for our study, of course, but it's not so easy. And that's why I need like many approaches. I need to cover a lot of approaches to reach more indicators or more assessment. I will show you it after. So just before this, this resilience or vulnerability is not the same, is not constant in the time. If today my coast is vulnerable, okay, maybe tomorrow or after 1 year, the vulnerability is different and its resilience is different. Why resilience is changing in time? So simple, because the resilience, it depends on the physical drivers, and the physical drivers change in time. All our physical drivers, sea level rise, waves, run up, and everything, storm surge, are operating, at different time scales. You see here, like we have the spatial scale and we have the temporal scale. We have so many like components. We see many colors. So in the spatial scales, like from the turbulence, okay, until the like Nino climate change, and in time we have like from the storms, okay, to the climate change or the turbulent change, the climate change effect. So you see, like we have different scales, and the problem here in our coast that this result, the resulting response or its response, it depends on a complexity or an integration between different scales. So all drivers are different in time, have different scales, so the resilience is changing in time. So we have spatial scales from the global scale to the local scale, and then from the scale of the storm here to the scale of the long-term trend, okay, climate change. Coast, our coast should to face to extreme storms, okay? I take extremes. How can we define an extreme? How an extreme is defined? So I will take an example. Before taking an example, what we can see in internet and everything in ChatGPT, like an extreme is a likelihood of a given event occurring at an unusual intensity during a specific time frame. Unusual, what is the usual for us to speak about unusual? It's a very good question. Okay, so how can we define usual and unusual values? The variation changes in time and space. If today my extreme is one value, after 1 year my extreme is different. It's different, and we see because we have many effects changing in time, and the definition of this extreme is different. So I can take an example. We can take a time series here, and we can put some extreme, okay? And we can define a threshold, and we can say, okay, I will consider that all extremes are higher than my threshold. But the problem here is that this threshold can be good for one period and cannot be really adequate for other period. As we can see here, we see it's perfect, my threshold. But here we have a lot, you see, we have a lot of moderate scenario that not really extreme. So what's happened? And how can we solve this? It's basically, here we use many approaches, statistical approaches based on GUV distribution, like generalized extreme values, spot values, and many others to estimate the extremes. I am wondering here, okay, how can we estimate this extreme if it is changing in time? And what is the relation of extremes with other mechanisms in our planet or our atmospheric circulation? Questions? Okay, so what we can do, what we need, like take a long time series to have more data, and it's crucial to understand the trajectory of the evolution in time. I can take here to access to such data. We have like many approaches. The simple one and that we know, it's like take some measurements from all variables, okay? Measurement in situ measurements. I have an equipment, and this equipment is deployed in one site, okay? In one site, one point, it's very local space and time, and then we can recuperate everything. Perfect, that's really perfect. But I don't need one point. I need to specialize everything in my area to understand how the energy is changing in the space, but in time as well. Okay, so another approach that's very important approach is the use of satellite data. And here we can use altimetry data and imagery data. So the most important point here that with satellite data we can obtain measurements in all the world, in all our plan. But the problem is that the time resolution is not like in situ measurements. Time resolution is like less significant. Okay, for example, I cannot take each 1 hour. Okay, maybe each day it's 5 days, each 21 days. It depends on the satellite. So here I will just give you this insight. It's very important. Using in situ data is not enough. Using satellite data is not enough. The main concern here is to combine many approaches, including within the satellite data, we have many missions. I can mention topics, JSON, MVSat, Cleosat, and others. And for each mission, we have a period of where the satellite is operational. So combining or integrating the different satellite missions, it's very important to have longer series, okay, with high temporal steps or high time steps, okay? And then combining these or comparing, validating all our satellite data with in situ measurements is crucial, of course, to be sure that our measurements is very well calibrated, and by this way we can use them. So, another example that you can see here that I have my measurements. You say that wave boys here, I take 8, and we have the time series, and the black lines is the time series, but I have a lot of gaps. We see a lot of gaps, like the red parts are a lot of gaps. So in this case, the combinations of in situ measurements with satellite data is very important. We can solve this problem. That's why. That's why we speak about the combination of the different approaches. Okay, so we have our physical drivers or extreme physical drivers, storms, and these storms will arrive to my coast, and my coast will maybe vulnerable or not vulnerable, and depending on this, we will see what's happened with its response. And we have many approaches to measure it. In situ measurements, we can get to the field, take some equipment to measure, but also we can use satellites as I show in this slide. So, what is the occurrence of satellites or of all altimetry in the coast? That's a very important question. Are we able to obtain really accurate information to be sure and to be used for models, for calibration models and others? That's a question. Why? A very common questions. Why? Because coastal areas are very complex, and we have, as I said you in the beginning, we have a lot of drivers, and the non-linear interaction between drivers enhance the complexities. First. Second, it's interaction zones where the depth is very reduced. And when depth are very reduced, we have the problems of layovers in the satellites, and it could make some problems to have accurate data. So here, if we can look for the previous works, during the last 3 decades, radar altimetry were providing accurate data sets. True? Okay. But where exactly? In the ocean, in the neutral, close to the coast? So, when a satellite observes the coast, what we observe exactly when floods happen? We observe this. If we take an image, okay? For example, I take Nice coast, Sentinel-2, during the storm Alexandra, I guess the name, and we see here the plume, the sediment plume here. Very important. It's very visible, okay? It's really clearly observed, like we have sediment plumes in the coast because all systems here are connected to rivers. So it could be used, it should be used, or it's an excellent tool to understand or to quantify these sediment plumes. I can present here les dunes de Pilat dunes in Bordeaux, in France, in the northern side, by Pléiades. And we see fantastic structures, very well structured, okay, like the dunes, okay, and we can look for the migration of dunes. Then we see Arcachon Bay in Bordeaux as well, and you can see all the fluvial systems. So we are able to know the area and the water volume related to this. We see like in the Delta of Mississippi using Landsat 5, using the infrared. That's why we see the vegetation red, and then Pléiades to see the Mayotte Islands. Fantastic. Okay. So, is it enough? That's the questions. Is enough to a certain limit or to a certain extent? Sorry, it depends on our studies. But if we need really a long-term variation of the systems to understand the trajectory of the evolution of the systems in response to climate change, we need to combine different approaches: in situ measurements, observations, okay, with satellites or observation from space, and then all numerical approaches, based on mathematical equations, and the combination between all components toward the development of digital twins model. That's an excellent tool to understand the evolutions of our systems, and especially to help us then to implement our adaptation strategies of our solutions. So maybe I can present here some examples of use cases to look for or to understand really how can I take our project to start from the beginning until the end, and to assess its resilience or the impact of hazards and the resilience. So I will take many, all such events or all such use cases that have been performed in the framework of many projects, international, national, but basically funded by special agency, because we have a lot of satellite data used in all projects. So, this one. So, I will take many examples: Mexico, Mississippi, Argentina, Senegal, in Spain, and in France. So I will start by the first one. Is France, is our lovely sites in Normandy, Etretat. And Etretat, it's a very touristic beach. It's a gravel beach, it's not a sandy, have gravels. And it's a pocket beach between two bedrocks, okay? And this beach is very exposed to severe storms. So when we have storms coming from the Atlantic, these storms go foresight to the coast, and it's like we have many changes or many modification. Okay, so with the syndicat mixte de la Seine-Maritime, we have a project together, and they have funded the implementation of a video camera. As you can see here, 3 cameras, and each camera will look for one sections, okay, of the beach, and the combination between all sections will give us a panoramic view, as we can see here. That's fantastic, and we can obtain images each 10 minutes. So we can have all information on the beach each 10 minutes. Fantastic. So I am able to survey or to track my beach for a very high monitoring each 10 minutes. So I can see here a video, we see, like it's a chart line each 10 minutes, okay? And we have assessed there for extreme events. We are not able to get to the field to do some measurements in the field. So what's happened? That we are in our office and we can consult the websites. On the websites, we have all the variation in my beach. Okay, and what we have done, we have connected all the morphological part we see in the below with the hydrodynamics, and we see the peaks, the peak of the the peak of the storm, okay? So it was really useful to understand the morphological response of our beach to this storm. And this storm, it's occurred in, you see, in February 2020, just before the pandemic, named Kiara storm. And then, to understand this resilience, vulnerability, so we have to look for the evolutions of the beach, of the coastal systems in times. So what we have taken here, we have taken a lot of images from satellites, Sentinel-2, Landsat 6, 7, 8, okay? And we have combined all the missions. And what we have done, we have assessed all the patterns, the evolution of the shoreline, like retreat, advance, accumulation, erosion. You see, like here, from the red to the blue color. And we see here, like, many patterns in time, in space, along the beach, and in time. So we have shoreline changes in time. And then we see, like, the green part, or the green points, like all the storms. And in Normandy, we have many mechanisms very known. Like, we have not one storm, no. We have a clustering of storms. Like, storms are one other one, and during the winter seasons, we have a lot of storms, one after others, okay? And that's complicated because the system cannot be recovered after one storm, and another storm is coming, and etc. And it's complicated. So I take here the storm Kiara, and what we have done here, we have taken the satellite images, Sentinel-2, and we have assessed the changes of volumes before Kiara and after Kiara. And we have mapped changes in the volume along the beach. And then it was in the framework of the PhD, my PhD working with me on François. What we have done as well to complete this, because Sentinel-2 we have like a resolution of more than 100 meters is not enough for us. So we have implemented some UAV campaigns, like drone campaigns, to understand the changes on the slope of the beach, and basically the distribution of the gravels. Where? Because in such systems, the distribution of gravels change the slope. Okay? And here the problem that when we have gravels, not sands, and the disposition of the gravels, one close another, we have space between gravels. And such space, it's very important to be considered in our models. Why? Because when we have a lot of volumes flooded the area, this water will be infiltrated in the space. You see, like, it's a very complex systems, and that's why we need to look for the distribution of gravels and the changes of slopes. Here, yeah, and we see here, like, with deep learning algorithms, we have quantified the distribution, the size of gravels, the distributions, and then we have looked for the slope. So what's happening here? We have, I told you that it was just before the pandemic, this storm. So we were at home. We hadn't access to the field, I remember. So we have used all this to understand what's happened and what is the impact of these storms compared to the trajectory of all the systems before. And then we have like looked for the changes of the slope of the beach and what is the time required for this beach to be recovered, like to be stable, because here it is unstable. So the beach needs a time of adaptations to recuperate its equilibrium state or stability. Okay, and here the time of stability is the system was resilient. The time required for recovery, it's basically 3 months. So after 3 months, maybe more, because after the pandemic, when you were in Etretat, everything is okay, and the gravels are well distributed, and the system has recuperated its equilibrium state. Okay, so for these storms, what we have done as well, we have used like local campaigns as drones, other satellite data, and we have covered these with modeling. So we can see here the English Channel here, it's our side, and Etretat is just yeah, you see like here, okay? So I'm sorry, I cannot use the light. So we have used like some altimeter tracks, you see like all the colors, and we have extracted all the satellite altimetry data during the storms, okay? And such altimetry data were useful to calibrate our numerical model here, you see? And this numerical model is to look for the evolution of the storm in the time and how the energy coming from the Atlantic will be modulated in the basin and responsible on the overwash of what or close to the coast. So we can, so here we have done for at local scales. Here it's Etretat and other system Haute-sur-Mer, and we see here the concentration of energy. See like the different colors and the arrows in the direction of the energy and the concentration of energy along the system using SWAN model here. So then for such systems, we have assessed the extension of flooding if we consider 1 meter of sea level rise, like the projections of the IPCC reports until 2100. And we see, like I will be fast here because we see like the flooding here, we have mapped all flooded area from green to red area. The red area when the flooding is most important, and a green area when the flooding is not so important, okay? It's like the current state of the beach. And here we have considered 1 meter of sea level rise. And we have looked for the difference between like what's happened on our hazards when we consider 1 meter of sea level rise. We have basically more than 25% in fluid extent. It's incredible. So we have more flooding, but it's more than 25% in the extension of flooding in coastal areas. In the case of Normandy, of course, it will be different for other cases, for other beaches. Then I moved to Spain, where I have done my PhD. But I worked my PhD on Barcelona beaches, and I developed a model to understand how beaches can be resilient and can be recovered after hazards like storm. So we focused on the different beaches in Barcelona, Barceloneta, Somorrostro, Navalcarria, different small beaches, but there are different like response and activities. So what we have used here, we have used analogous camera systems, and these systems show us, you see, like we have the image, oblique image from the camera, and then we have rectified the image. We have digitalized or identified the blue point, the blue point in the image, like the shoreline, and then we have construct or build the time series of this evolution during a long period, okay? And then we have used this time series to build or to understand the evolution of erosion and accretion patterns along the beach, as we see here, and in time. And you see, like, we have different patterns. The red from erosion to accretion is in blue, and erosion is in red. So we have heterogeneous behavior along the beach. And in time, of course, for winter seasons, we have more energy and more erosion. And during summer seasons, we have like calm conditions. And here we have developed a model for estimating the evolution of the beach, as we can see, and we have calibrated with the observation. And here, the most important things here, that we have used some physical concepts, chaos concepts, here to understand the time required for the system to recuperate a new stability. Like if we have, you see like the curve, like R0 here, and you have the evolution in the model. So if I perturb the initial positions here, we will okay, the system will evolve, but at final stage, it will reach its final position. So we have a time required for the systems to reach its stability, what we name like the recovery time or time of stability. And that's why we can do for resilience. We simulate our models to understand if we have this magnitude of perturbation, what is the time required for the bridge to reach the stability. And then I will move to CADIS. And in CADIS here, it's a very complex systems. And it's basically work done by colleagues from Argentina and from CADIS. And here we have the Bay of Cadiz, and we have different systems, you see? And all systems, coastal systems, all points, like Faro, Antilla, Camposoto, we have 3 beaches exposed to the same energy. So the same energy coming from the Mediterranean beach are coming to are affecting the beach. But the resilience of all systems are different. Why? Because the characteristic, the internal characteristics of all systems are different. And we see here that we have many touristic settlements, urbanizations, like nature reserves, vegetations. And in each systems, when we have used Sentinel 1, 2, other drone campaigns, we have mapped all the vegetations in all of the systems, and we have also mapped all the urban zones. So we have different densities of vegetations, of urban zones, and this component or such components has affected the resilience of the beach. That's why for the different systems we see like different evolutions, and this limit or this threshold of resistance, it's different for the different beach. Basically, for the density of urban settlements and vegetated dunes and marshes and many other like components, very related to the systems. Okay, it's very local. It's not related to physical drivers. So physical drivers are important, of course, to be assessed, but we have to know really the characteristics of the systems to understand its vulnerability and then its resilience. And then I moved to another, we traveled to USA, to Mississippi, Gulf of Mississippi. So we have, it's work done with some colleagues from GPL, Jet Propulsion Laboratory. And we have here small delta, okay, works like delta, connected to many fluvial activities at Chapalaya and others, okay, and it's a very complex system. Why? Because we have interactions between fluvial part and it's a microtidal systems. The tide is very small, but the problem that the waves are very important. And when we have hurricanes, like Katrina hurricanes, Rita hurricanes, it's very vulnerable, the systems. So what we have done there is, we have, of course, assessed all the driver, the physical, or the energy produced or induced by this hurricane, but we have assessed as well all the characteristics of the systems, basically the wetlands, and we have used Sentinel-1 for mapping all the vegetated area and all the wetlands in the systems. And here our objective, how the wetlands are important to reduce the energy of all the risks. And here what we can move here as well. So what we have here, we have a very nice simulation here, and we see the Wax Lake. We see our shores, the black arrow, and we have many other arrows related to the marine drivers like tides and winds and everything. And here we have just a simulation how the system is changing in time, like wet dry zones, the flooded area. And here we have considered all the wetlands mapping and the vegetation and their effects on the reduction of energy. And what we have done here, yeah, we have taken 2 examples of simulation. The first one vegetation, we haven't considered the vegetation. Okay, and the second one, we have considered this mapping of vegetative area, and what we have seen that the energy, you see that between the blue, the red, and the green curve, that the energy it's reduced within the presence of the vegetation, and this reduction could reach 35%. I don't know if it is here. No, it's basically here the infragravity waves between non-vegetated conditions, the red ones, and vegetated conditions, the green ones, and we have really reductions of infragravity impacts of infragravity waves in the Wax Lake Delta when we consider all the wetlands and vegetations. We travel to Mexico now, and then I will take this. It's a work done in La Universidad Autónoma de México, and a very nice work here because they have assessed the impact of a dike, okay, and the impact of this dike on the evolution of the system. They have deployed a dike in their coast, and then they have deployed a lot of campaigns and a video camera to look for the role of this dike on the changes of all the hydrodynamics and the sedimentary systems. So that they had one, you see like the dike here. And here, for example, the dike for the first 3 years, that's fantastic, everything is okay. But then have like many other negative impacts in relation with the changes in the depth, changes of the sediment patterns, and all other problems that have been enhanced and exacerbated by the increasing of urbanization. So the density of urbanization has increased, like what we have assessed by satellites, and integrating this urbanization in the model has been done to assess the vulnerability of the systems. And we see that the vulnerability is changing in the space. When we have red colors, the system is very vulnerable, okay? So cannot be resistant or he cannot be resilient. And other parts or segments, the vulnerability is less important and the resilience is more important. And then we travel to Argentina in la Universidad Mar del Plata. Si hay argentinos, por favor, disculpa, in the seminar. So Mar del Plata, sorry, and with some many in this group, they have assessed the vulnerability of the system and the hazards, especially when we have increasing of urbanizations. So they have done this for like during 40 years, okay? And they have demonstrated that the increasing trend of all urbanizations enhance the impacts of storms in such systems. Like they have many deforestation, economic growth, touristic urbanization, expansions, and all that components decrease the resilience of the systems. Like we can see here. And then they have done the forecasting of land use distributions for 2020 to look for how the systems in 2020 can be, or to which extent could be resilient. And they have noted that it's really the vulnerability is more important. And now it's a work done with my colleagues, funded by Space Coastal Observatory in Normandy University, related to another company, Resilience, in Toulouse, and held by University of Dakar and CNES. And for this, we have used Pleiad images to build the intertidal topography, as you can see here. And this intertidal topography was useful for mapping all vulnerable areas, like vulnerable areas, the red points. And then we have developed some numerical simulations to understand, combining the model with the land use we see here, like like all land use and urbanizations has been included in our model to look for the extension of the water in such area. So some areas where the density of urbanization is important, so the extension or the vulnerability is more important. And we have done the same for pollution under 2100 reduction of RC3 8.5 to look for how this extension of water is impacted. So we have like some results of the model have shown that we can reach 1 kilometer from the coast, and the water can be in the coast until 1 kilometer, okay, and until 4 meters of depth. So it's very very dangerous, and it's very critical. Yeah. So just to say that all the work that I presented is not my work alone. It's my work, or in some project that I heard, or with other colleagues. It's like insights of all the points or all the actions handled in our universities or in collaborations. So thank you for my colleagues to all these insights. So as I told you here, all the examples show that the coupling between the different approaches is very important, from the models, satellites, and in-situ observations, to understand really and to look for this resilience. So an example to confirm what I am saying, we use satellites for intertidal topography. Why exactly? What we need is when we need to look for the impacts of coastal hazards in some coastal system, very complex. So we have, or it's useful and crucial to use a very high, a very good bathymetry, significant bathymetry with high resolutions to understand for changes in depth and in slopes. So we can use satellite imagery to look for the different, the intertidal topography. And here, it's very important, and I told you, it has been done at Cachambe, my colleagues, BDV, and other systems in China here. And to understand the evolution, of course, but it's very important that we use as an input for enhancing the accuracy and reduce the uncertainties of numerical models. So that is the first part of my conference. I am not sure if I am good in time or not.
I think we have a so. Yeah, I think so.
If you have questions, yeah.
Yeah, for sure. But afterwards we have a coffee break, I think.
Okay, but
After questions.
After questions, okay.
Yeah.
So we can.
Yeah.
Okay, so I don't know everywhere if we are. I don't know because. So I hope that you stay with me, and I am happy to answer to your questions. So I have to maybe. ¿Cómo hablan aquí? ¿Pueden hablar o cómo?
Yeah, they should.
Deberían de tener el audio.
O sea, no hago nada.
No.
Solo escucho.
Solo escuchar si alguien tiene alguna pregunta.
And you can ask questions as well. I hope that it's interesting for you.
I always have questions.
I have many questions, but I can ask you later. If not, I can ask my first question. I can ask one question.
All your questions are welcome.
Because I know her, you are priority to you.
Oh, don't worry.
How? Because when you have a cost, you choose some sites, and in general, how do you decide? Okay, we stop here and we stop here, because it's an open thing.
It depends where.
For the American model.
Yeah.
Yeah.
Even for the study, you decide.
But it depends where, and it depends because we cannot show the site. Okay, venga, vamos a leer esto. No, it's not like this, you know. We cannot show the site. We work in the framework of programs. Okay, and for example, the ministry, or I don't know, or the environmental organism come and okay, I am interested to these sites here, okay, because we have many and there are a number of issues and a lot of vulnerabilities. Okay, so for example, okay, so we have to define our sites where the issues are important and the physical process that we need to solve in one site where it's possible to go. First part. Second part, we work where data is available, and what's work it's normal, you know. So it's a balance between many things. But for example, for projects, not only research one, because we can solve our theoretical research question. That's fantastic. If you have funding to do it, fantastic. But in some times, as you know, we can solve our research questions through some projects because we need the money. So, for example, I don't know, the Port of del Estado, okay, we are interested to do this, and I am interested to solve this. So it depends on many things, okay?
And then how do you decide, for example, I don't know.
If I was thinking in terms of
Modeling,
numerical modeling, yes, in terms of the
so for example, I come from Cadix. I said I'm interested on be sure that my coast will be there in 100 years. I'm the mayor of Cadix, and then you decide you stop in because you can study all the coast around Cadix, or you can do something really 100 kilometers or maybe 10 kilometers or maybe.
If we go with numerical models, for example, in the pelagic model, we work on relation, one which in Ireland, okay? So we cannot just take where is the relation there and put our model there. No, we have to take the price, you know.
Where do you start?
Yeah, it's depending on the physical drivers as well, you know, the wind, the direction of wind, the waves, and then, you know, for example, in the period of Carlos, he was interested to the English Channel. He has not just taken only the English Channel, he has taken all the Atlantic, the North Sea, all where the drivers are coming. Because we cannot take the drivers after the deformation of the driver. No, we have to take the driver from the beginning and simulate the drivers, sides, wind, everything, okay? To maintain that until the shore, okay? It's for models. For observations, when we take satellites, of course, for example, we can take satellites, it covers a very big system or very large system. We can use this. For example, I can give an example in Nice, Côte d'Azur, and Monaco, it's closed, okay? So there are projects to use the satellites to understand the multi-time scale variability of the shoreline. We will use the image. So the image cover Monaco and Nice. So we take both of them, you know. So we are able to take a very large part, you know, like domain. Yeah. It depends on what we are doing, but with models, of course, we cannot just model the part of we have to take everything, and it depends on our because that's why understanding the model it's very important. Understanding the site, sorry, it's very important to know how or what are basically the physical drivers controlling the system. Yes.
I have a naive question, because it's not my interest, okay? But for the cost of functionality you showed at the beginning,
Yeah.
why there is nothing about the geochemical cycle, like carbon? Because this is a place where you can store a lot of carbon, like in the car.
Very good question. But for me, I'm not an expert as you in carbon. For me, this it's including habitat and
No, it's okay. Habitat is
it's included for me. It's included the same.
Yeah, okay.
Is there
Maybe because it's very important, carbon, everybody knows that.
Yeah.
Maybe you can separate habitat and biology.
But I'm not expert, but thank you very much for your remarks. For me, the same. Venga. But yeah, of course.
Because you have the second and
For
the
the
second
section of
stuff,
carbon, yeah.
the different stuff moves.
The storage of carbon.
Stuck and tightening.
No, but maybe because I will look in the chat maybe.
Yeah, it's a beginning and maybe the second slide. Just like,
C'est où le truc?
remember.
Ah, c'est ok. Alors, non, ici. Non.
Maybe you can ask if someone is in Argentina, but
Very simple.
No problem. It was fine? It was fine? Yeah, sure.
Yeah,
20 seconds.
no, I don't know.
All online people, it was fine. It is interesting for you. Are you interested to all such subjects? Are you here?
They have already started.
Are you sleeping?
Yeah, I think they are.
Once I see it, no.
The only thing I just have is just like an addendum to what Imen says, regarding in terms of the needs of your domain is that based on each kind of model you're working on and what you want to look into.
Yes, interesting. Thank you.
So
Okay.
for example, now if you're looking into wave overtopping, the
It's very interesting.
extent
I
of the
read the
domain
paper.
is going to be different. If you're looking to like the gravity extent of the domain is going to be different based on how the developer built all this model. And another thing is in terms of the width is that they call something like I've forgotten the correct scientific word for this, just like a blind spot. Like, okay, let's assume the wave is coming at an angle like this, then there is a blind spot around it. So which whereby any result you're getting here does not really, it's not really that accurate, then it's not true.
Because more features you are right. You need to know what's here to. Yes. So it's more. For example, instructions are no. Okay, so these photos and these graphics.
What does that?
It was there, yeah. It's
Okay.
Sí, sí, sí. A ver, vamos a parar 20 minutos. Paramos unos 20 minutos para descansar. Gracias.
Okay.